We've been looking at graphs, we've been analyzing graphs, and now we're continuing to look at graphs and determine different aspects about them. And a couple of the things that we're looking at in this lesson is whether a graph is continuous, meaning it's a smooth curve, or basically that you don't have to pick up your pencil in order to draw the whole thing. And we're also going to be talking about end behavior, meaning how does this graph behave as it goes all the way to the left, and how does this graph behave as it goes all the way to the right. So first we're going to talk about whether a graph is continuous and how we can test whether it's continuous. And if it's not continuous, we can test what kind of discontinuity it is. So there's infinite discontinuities where it's either approaching positive infinity or negative infinity as it approaches the point of discontinuity, or there's a jump discontinuity where there is a value for the f of c, if you will, of where that point of continuity breaks. So there is a function value, but as I approach that value from the left and as I approach that value from the right, the values are two different things. And then finally, those two discontinuities are considered non-removable because just making the graph defined, like a lot of times a graph will be discontinuous because there's something that's undefined at that point. Fixing that point doesn't fix the discontinuity in a non-removable discontinuity. And so then at the final cluster of bullets on your screen, you basically see the test for how to check whether a function is continuous. If I plug in a value for x, I actually get an answer. That's valuable. And as I mentioned earlier, my f of x has to be approaching the same value from both directions. And if all of the stuff that I've just said sounds like a bunch of gobbledygook, I get that. And of course, it's my hope that as I go through the next few examples, that gobbledygook becomes a little bit more clear and the language that we're using becomes more manageable. In this example, we are identifying whether a graph is continuous at x equals 0. So my graph is f of x equals x to the third. Now I don't have a graph, but it is asking me to use the continuity test. So the first part of the continuity test is to check whether f of 0 exists. So can I find the f of 0? If I plug in 0 for x, can I take 0 and raise it to the third power mathematically? Yes, I will get 0. So that's good. The second and third part of the test for continuity are to check what f of 0 approaches coming from the left and coming from the right. So here's what I mean by that. If I'm considering 0 on the number line and I am approaching it from the left, then a couple of numbers that I could test for x might be -1 and -0.5. Okay, so I'm going to plug in -1 for x, I'm going to plug in -0.5 for x, and part of what I'm testing for is, am I getting closer to 0 as I plug in those points? Okay, so f of -1 is -1 to the third power, which is -1. Well, that's kind of close to 0, so that looks promising. And then I check f of -0.5. And if this is going to look promising for f of 0 to be a point of continuity, then my answer is going to be even closer to 0. Okay, so I take this negative 0.5 and I raise it to the third power, and I get negative 0.125. Oops, too many negatives. So as I'm approaching 0 from the left, I am in fact getting closer to f of 0 being 0. So that looks good so far. Now I'm going to approach it from the right. And as I approach it from the right, some numbers that are really close to 0 might be 1 and positive 0.5. When I evaluate f of 1, I get 1 to the third power, which is 1. When I evaluate f to the 0.5, I get 0.125. And once again, as my x's are getting closer to 0, my function values are also getting closer to 0. So that's another part of the continuity test. And since these are approaching 0, and these are approaching 0, and this is 0, that means that the function is continuous at f of 0. My bottom line answer is that it's continuous at 0. And this whole process that I went through was the justifying using the continuity test. Take a moment and work through the your turn below. Once again, we're determining if a function is continuous at a given x value. We're justifying using the continuity test. This time, if it is discontinuous, they are asking us to identify what kind of discontinuity we have. Now this time I've added a table, and I think this might help make things make sense if the last example of testing for continuity was a little bit strange. Okay, so once again, the continuity test requires that I find a function value. So if my x value is 0, then I'd be finding the function of 0, and I'd be plugging in 0 for x. So that would be 1 over 0 squared, and that is undefined. So since there is no function value at the x value of 0, right away I know that it is not continuous. However, since the problem is asking us for what kind of discontinuity, we're going to continue. We've already talked about what kind of x values approach 0 from the left and what kind of x values approach 0 from the right. So I'm just going to use those values again because they're good values. -1, and -0.5. So I'm going to take -1 and plug it in. And I would have 1 over -1 squared being 1. And I'm going to plug in that -0.5 and square it, and I'll have the function of -0.5 being 1 over -0.5 squared which is 4. So as I'm getting closer to 0, like -1 and -0.5 are getting closer to 0, my y values, my function values, are increasing. And so it looks like that might be increasing by quite a bit. Let's look at this function coming from the right. So coming from the right, I'd be looking at 1 and 0.5, and using your number sense, I would hope that you'd notice that I end up with the same two values, 1 and 4. So because as I approach 0, I am getting bigger and bigger, this is an infinite discontinuity. This time I'm testing for whether the function is continuous at 2. So my x value this time is 2. And in this piecewise function, I'm going to take that 2 and plug it into the second piece of the function. So f of 2 would equal to -2, which is 0. So f of c does exist. F of 2 exists. Now I need to approach 2 from the left, and I need to approach 2 from the right, and see if those values that they're approaching are also 2. So approaching this from the left, I have 1 and 1.5. And when I find the function of 1, I'm plugging it into still the second part of my function. So I have 2 minus 1 is 1. And then in the second one, I have 1.5. And I'm finding 2 minus 1.5. Whoops. And that gives me 0.5. So as I'm approaching 2, my x value that I'm testing, as I'm approaching it from the left, I am getting closer to my function value at 2. I am getting closer to 0. So that looks promising. Now I have to approach it from the right. So approaching 2 from the right would be 3 and 2.5. So let's find the function of 3. When I find the function of 3, I have to plug it into the first part of my piecewise function. And when I plug it into my piecewise function, I have 5 times 3 plus 4. And that is 19. When I find my function value at 2.5, I have function of 2.5 is 5 times 2.5 plus 4. And that's 16.5. And that's still not very close to 0. But just in case you are maybe the kind of student that would question, which is fine, and say, you know what, it's not really close to 0, but it is getting smaller, I'm not quite sure if it's not approaching 0. So let's try one more point. You see that I've written down 2.1. That's a little bit closer to 2, approaching from the right. So we'll see what happens here. The function of 2.1 would be 5 times 2.1 plus 4, being 10.5 plus 4 is 14.5, and that's still not very close to 0. I don't think that this is really approaching 0. It might be approaching 14. So even though I have a function value at 2, we've determined that it is not continuous, and notice that while it's approaching 0 when I'm coming to 2 from the left, when I'm approaching 2 from the right, it's coming from a completely different direction. So this is a jump discontinuity. Another thing that we're able to analyze within a function is if we see, for example, that the f of a is one sign and that the f of b is a different sign, well, somewhere between positive numbers and negative numbers, there's 0. So what this tells us is that if f of a is one sign, and f of b is a different sign, then there's a 0 for the function, or an x-intercept for that function, between a and b. So in this example, we are finding the interval, the 2 consecutive integers where we can find a 0 between them. So this is another instance where a table might be helpful. Okay, so we're going to take these values for x, the -3 all the way up to 4, plug them in and find our function values and see where the signs change. So when I take -3 and plug it in, I have 3 squared, which is 9, minus 6, which is 3, over -3 plus 4, which is 1, so that's just 3. When I plug in -2, I have -2 squared is 4, 4 minus 6 is -2, and I'm dividing that by 2, so that's -1. So right away, I see one integer. But I might have more, one interval, excuse me. -1 squared is 1, minus 6 is -5, over 3. So that's still negative. When I plug in 0, I've got -6 over 4. That's still negative. I plug in 1. I have 1 minus 6 is -5 over 5. That's -1. That's still negative. When I plug in 2, that's 2 squared is 4. 4 minus 6 is -2 over 6, that's still negative. Plug in 3. I have 3 squared is 9. 9 minus 6 is 3. Over 7. And that's positive, so I see that there's a change here. And finally, they did ask me all the way up to 4, so let's go ahead and test it. So I take the 4, I plug it in, I've got 16 minus 6 is 10 over 8, that's still positive. So my two intervals between which I would find a 0 is I'm going to find a 0 somewhere between negative 3 and 2 and positive 2 and 3. In part B, we're doing the same thing. This time, my interval is negative 5 to 0. So I start at negative 5. And you're plugging that 5 into that trinomial, or polynomial. So I really hope you have a calculator. So plugging the values in, I have negative 1,000 minus 50 plus 25 minus 1. So it's negative 1,026. And one of the things that you might become adept to in your number sense is to think to yourself, you know what, that is really, really, really negative. And when I take this negative 4 and I raise it to the third power and I'm subtracting a whole bunch of stuff from it, I just don't know if I'm going to be getting positive yet. So maybe instead of plugging in negative 4, maybe I plug in negative 3. So again, using my calculator, I've got negative 216 minus 18 plus 15 minus 1. And I'm still pretty massively negative. So maybe I don't want to plug into negative 2 yet. Maybe I want to try negative 1. So I plug in negative 1. And I get negative 8 minus 2 plus 5 minus 1. And I'm getting warmer. I'm at negative 6. And then I'm going to plug in 0. And when I plug in 0, I still have a negative value. Well, I tried to save myself a little bit of time, but I should probably try those other two values and see if there's a 0 kind of sneaking in between there. So I plug in the negative 4. And I've got negative 512 minus 32 plus 20 minus 1. Nope, that's still negative. And it's looking like maybe we don't have a 0 in this interval. Let's double check with that negative 2. and I have negative 64 minus 8 plus 10 minus 1. And no, I don't. So what I've found is that nowhere from negative 5 to 0 will my graph cross the x-axis. Nowhere will I have a 0 between negative 5 and 0. No zeros in this interval. Finally, we come to talking about end behavior. And with end behavior, the main thing that you're looking at is, as I go further to the right, is my graph going all the way up or all the way down, or does it look like it's kind of flattening out towards a number? And the textbook divides them into two categories: graphs that approach infinity and graphs that approach a number. So you see that these examples are titled graphs that approach infinity. And it's asking us to use the function to describe the end behavior. So the way you might want to notate this is maybe with another table. In my table, I'm going to have, as x approaches, f of x approaches. So what I'm looking at is, as x approaches positive infinity, in other words, as x goes further and further to the right, my function values appear to be also going to positive infinity. Because as I go further and further to the right on my graph, I'm also going further and further up in my graph. And so I look at the graph in the opposite direction. As my graph approaches all the way to the left, as x approaches negative infinity, my y's are going all the way down. So my function values appear to be going to negative infinity. And the instructions ask us to support the conjecture numerically. So as something approaches positive infinity, I might choose to pick a very large number to plug in for x. So I might pick an x value of 1,000. If I plug 1,000 in to that function, I've got 1,000 raised to the third power. Is your calculator bursting at the seams yet? And then minus 9,000 plus 2. And so that's a very, very massive number. And what I would hope starts to happen, again, in your personal number sense, is that you realize that if I take a very large number and I plug it into here, that x third, when I subtract that large number multiplied by 9 and then I add 2, that's almost negligible. I could almost ignore that and kind of approximate how huge my number is going to be. So if x is 1,000, y equals a lot, let's say. And if I go in the opposite direction, if I approach negative infinity, if x is negative 1,000, once again, I'd hope that you'd have the number sense to realize that y is a big negative. And so we have supported our conjecture numerically. Doing the same thing in part B. As x approaches positive infinity, f of x approaches. So you're looking at this graph, And as the graph is going further and further to the right, I see that my y values are going further and further down. So that appears to be approaching negative infinity. And as x approaches negative infinity, as I'm looking at my graph going further and further to the left, my function values, my y values, appear to be going further and further up towards positive infinity. Supporting it numerically, if I have x equals 1,000, when I plug this into my calculator, 1,000 raised to the third power, I put a negative in front of it, divided by 4, that's still a pretty big number, negative-wise, and then I add 1,000 squared times 3 divided by 4 to it. That's still a very large negative number. And because I'm going to have minus a negative this time, I add 1,000 divided by 2, which is 500. I still have a very negative large number. It's actually y equals negative 24,924,000. Oh wait, no. I put my comma in the wrong place. That's how big this number is. So, once again, this is a big negative number. And if I plug in x equals negative 1,000, it's going to go the other way because a negative raised to an odd power is going to stay negative. That's going to be a very large number. So my y value is a lot. Here we're looking at graphs that appear to be flattening out and approach a certain number. And so that gets a little bit more challenging to look at. We might want to use the same kind of table. As x approaches positive infinity, what's happening to f of x. All right, so as x approaches positive infinity, as my graph is going further and further to the right, it looks like somewhere between 2 and 3. And as my graph is approaching negative infinity, as I'm going further and further to the left, it looks like it's somewhere between 3 and 4. So we have something in common here, and maybe we have a hunch about where it's going. And when we look at the equation, maybe that hunch is intensified, but the instructions did ask us to support the conjecture numerically. So I'd like you to be in the habit of at least thinking about what this would look like in your calculator with very large numbers. Okay, so if I plugged in a very large number into this function, what I'd like you to notice is if I plug in a very, very large number, subtracting 2 from it in the numerator and adding 1 to it in the denominator, again, becomes negligible. So I can look at what's happening here. I'd have 3x over x, which would reduce to 3. So if I'm plugging in a very large number, the x's would cancel out and I'd end up with approaching 3. And if I was approaching a very small number, going towards the left, I'd be plugging in a very large negative number, but once again, it would cancel out. Okay, so my end behavior, I can conclude that it's approaching 3. Take a moment and work through the your turn below.